Today we will discuss about interference using air wedge. Using this phenomenon, we can find the thickness of many thin materials. So today in this experiment, we are going to find the thickness of a thin paper using air wedge apparatus. For performing this experiment, we want a travelling microscope. Speaking about it, it's called travelling microscope because vertical and horizontal motion is possible. So in this experiment, we will focus the travelling microscope and we will take readings from the main scale and vernier scale. Then we want a sodium vapor lamp, which is a monochromatic light source. Then what we wanted is a wooden box with a glass plate inclined at 45 degrees for normal incidence. Into this we will keep the air wedge setup. Speaking about the air wedge setup, it is of two optically plain glass plates aligned and one end is tightened with the rubber and the paper is kept in between the two glass plates in other end. There is a gap formed between these glass plates and air is filled in it. So it's called air wedge.
Let us move on to the working principle and basic theory behind this experiment before going to perform it. So, what is our experiment? Yes, interference by an air wedge. Now, all of you may have questions like, what is interference, what is air wedge, right? Yes. First of all, interference of light is the phenomena of multiple light waves interacting with one another under certain circumstances, causing in the combined amplitude of the waves either to increase or to decrease. The phenomenon of interference can be described with the help of wave nature. When two or more waves travel in the light at same space at same time, sometimes these two wave motions combine and some physical effect takes place. Interference is also such an effect. In simple terms, interference is the combined effect of circumstance caused by each individual wave at same place and at same time. This can be explained with the help of principle of superposition of waves. According to the principle of superposition, two or more waves travel through the same medium simultaneously. The resultant displacement at any point is the vector sum of the displacement due to the individual waves. Consider any two traveling waves with displacements y1 and y2 as you can see. If the crests and troughs of both waves are in same phase, the resultant amplitude or displacement will be the maximum, and this condition is called constructive interference. If the crest of one wave and the trough of the other wave superimpose, then the resultant displacement is minimum, and this condition is called destructive interference. The physical effect of superposition of waves from source vibrating with same frequency, amplitude and phase, that is a coherent source, is called the interference. Next comes the air wedge. What is it? Yes, a thin film having zero thickness at the one end and a progressively increasing to a particular thickness at the other end is called a wedge. If the medium here is air, then we can say it as an air wedge. The basic principle behind this experiment is that a thin film of air can be formed by two optically plain glass plates on each other at one end, and introducing a paper or a hair or any thin material as a thin spacer at the another edge, and this forms an air wedge. When parallel beam of monochromatic light falls normally on this arrangement, interference takes between the two reflected rays, one from the upper surface and one from the lower surface. These two reflected rays produce a pattern of alternate dark and bright interference fringes. Now, we will see in detail how interference occurs and how we can measure thickness of thin material using it.
When a light ray is incident
on the wedge from above, it will partly reflect back from the first surface and partly be transmitted and reflect back from the bottom surface. These two rays are coherent as they are derived from the same ray through the method of division of amplitude. This angle theta is a very small since the thickness of paper is very small. So we will assume this air wedge to be parallel. We have for condition for path difference delta f is equal to 2 mu t cos r minus lambda by 2 for interference in parallel films. Also we know delta f is n lambda for constructive interference. Equating these two, we will get 2 mu t cos r is equal to n plus half lambda. Similarly for destructive interference, we have path different 2n plus 1 lambda by 2. Equating these two, we will get 2 mu t cos r is equal to n plus 1 lambda. Here, the interference takes place between coherent sources, and the pattern obtained here will be of equal width. These fringes are also known as phase fringes. So already we have derived conditions for constructive as well as destructive interference. Here in this experiment, we will concentrate over the destructive interference. We have the condition 2 mu t cos r is equal to m plus 1 lambda. For making it simple, we will try to make cos r value to equal to 1. Somehow in A which we know mu refractive index mu will be 1. When cos r will be 1, when r is equal to 0. That is, when we make the incident ray fall normally onto the air wedge. Here, these are the two rays falling normally on the air wedge. So now we have mu is equal to 1, r is equal to 0. From that, we will get 2t is equal to m plus 1 lambda. For any arbitrary two rays, say xn, m3 and m3 and n3, where m is smaller than n, we will have 2tm is equal to n plus 1 lambda and 2tm is equal to m plus 1 lambda. From this, we can get the equation tn minus tm is equal to n minus m lambda by 2. From the figure, see, from triangle PAE, by using tan theta, we will get Tm is equal to xn tan theta. Similarly, from triangle PCD and PQR, we will get Tn is equal to xn tan theta and T is equal to L tan theta respectively. Then, since theta is a very small angle, tan theta will be very nearly equal to theta. So we will get Tm is equal to xn theta and Tn is equal to xn theta. From these two, we will get Tn minus Tm, and from this equation we can derive an equation for theta. We have T is equal to L theta. Substitute this Tn minus Tm and theta values in T is equal to F theta. You will get the formula for T, the thickness of thin paper, that is L lambda by 2 into n minus m by xn minus m. Here n minus m by xn minus m is nothing but the fringe width. So T is equal to L lambda by 2 beta. This is what we are using for finding the thickness of any thin material from this Air Wedge experiment. The experimental setup is like this, as you can see in the image. Here, in between the source and beam splitter, a condensing lens can be used to enhance the rendition of parallel beam of light rays, so that we can get a very clear fringe pattern. Since we are using a broad sodium vapor lamp here, we are not using condensing lens. So, shall we move on to the experiment? Yeah. Let us move on to perform the experiment for a more clear understanding.
Hello everyone, now we are going to perform the Interference from Air Wedge experiment. Here we got the traveling microscope, beam splitter, and sodium vapor lamp and the glass slab. So we will let see. Now I am on the sodium vapor lamp, which is a monochromatic light. Here we place the glass slab here beneath the beam splitter. Now we will try to focus the fringes. Guys, as you can see there, we see the fringes, dark fringes and as well as white bright fringes, and we see a cross wire which is used to take the readings. Now we will see how to take the readings for the tableau column. You guys can see now the air through a cross wire. It's been kept on a dark fringe. Now we will see the main scale reading here. It's at 6.85, and here the vernier scale is coinciding at fifth, that is fifth division, and now by moving the horizontal scale, we should move on to the second dark fringe to take the second reading. Now we are going to see how to take the readings for the distance between the edge of the contact of plates and the paper. Now here we have kept the glass plates below the traveling microscope, and we are going to focus the edge of the glass plates. Now as you can see here, the edge of the glass plates is being focused under the black cross wire. Then we are going to take the readings here. As it is 5.9, and we got the division as 5. Fifth division is coinciding with the main scale reading here. Now we will see to focus on the paper side. Now it is focused on the paper edge. Now we got the values as. Let's move on to the calculation part of the experiment. By performing as instructed, we will get the required readings to do calculations. Now, from table 1, we have mean fringe width beta equals to 0.1592 centimeters and mean fringe width of 10 fringes beta equals to 0.01592 centimeters. Now, from table 2, we have determined the distance between the edge of the contact of glass plates and the paper, that is L equals to 3.856 centimeters. We know that wavelength of the monochromatic light lambda equals to 5893 Armstrongs. And to find the thickness of the paper, we have the formula D equals to L lambda by 2 beta, where D is the thickness of the paper. Now, substituting the obtained values, we get the thickness of the paper as 71.3674 mu meters. So now we have learned how to perform the experiment interference from air wedge and the theory behind it. Thank you.